we're going to take a look at a process known as rationalizing the denominator. In other words, we're going to take a fraction and we're going to take all of the square roots out of the denominator and move them up top. We call it rationalizing the denominator because we're going to make the denominator a rational number. Now, what is the point of this? Well, really, at this point in time, it's really just tradition. Historically, mathematicians realized that if they wanted to do this division, they would be dividing by a huge decimal, which is very cumbersome and a real pain to deal with. However, if they rationalized the denominator, well, now they were dividing a nice number into a decimal, and that long division was much easier to do. The tradition is just stuck and held on throughout history. Let's take a look at a couple of examples to get an idea how we rationalize the denominator. The process can be a little confusing at first, so just hang in there. Let's take a look. In our first example, we have 2 over the square root of 5. Now, to me, rationalizing is the method of last resort. If I don't have to rationalize, I won't. And so the first thing I always look to see is if I can do any plain old division, and maybe that'll take care of the problem for me. Well, it does not. There's nothing I can divide here. So what I do is, notice I have a square root of 5 in the denominator. I'm going to take whatever that square root is in the denominator and multiply it on the top and on the bottom. So I'll multiply by the square root of 5 over the square root of 5. Now up top, when I do that, I have 2 times the square root of 5. That gives me 2 square roots of 5. In the denominator, I have square root of 5 times the square root of 5, which is the square root of 25. And if I've done it correctly, I will always end up with the square root of a perfect square down there, because that gives me a rational number. Now the square root of 25 is 5, so I have 2 square roots of 5 over 5. That's how you rationalize the denominator of a fraction. Now, why did I multiply by this, and why can I do that? Well, simply put, the reason I chose those numbers is that would force me to have a perfect square in the denominator. The reason I can do that is this is really just the number 1. It's a fancy number 1, because the square root of 5 divided by the square root of 5 is really 1. So really, I'm multiplying this fraction by a special number 1. Example 2, I have something similar. I have 3 over the square root of 3. And the first thing I look to see is if I can do some plain old regular division and take care of the problem. I can't. So I'm forced to use the method of last resort known as rationalizing the denominator. Down here, the radical is a square root of 3, and so I multiply by the square root of 3 over the square root of 3. 3 times the square root of 3 gives me 3 square roots of 3. And I multiply these 2 square roots together, and I get the square root of 9. And again, that's exactly what I wanted to happen, because now I have a perfect square down here, and the square root of 9 is 3. So I have 3 square roots of 3 over 3. Now I can reduce my fraction, the 3's cancel out, and I'm simply left with the square root of 3. You can check your answer by plugging the original and the final one into your calculator. You should get the same decimal. Want to take a look at another example? I knew you would. Let's take a look at example 3. We have 5 over 4 square roots of 18. First thing I look to see if I can do is some plain old regular division. Unfortunately, there's nothing to do. So I take the square root of 18, and notice I'm just taking the square root, and I multiply by square root of 18 over square root of 18. This is my fancy number 1. That gives me 5 times the square root of 18 in the numerator, and 4 times the square root of 324. And it just so happens that 324 is a perfect square. Square root of 324 is 18. And when I simplify the square root of 18, I get 3 square roots of 2. So 5 times the 3 square roots of 2 gives me 15 square roots of 2. And the 4 times the 18 is 72. And now I reduce my fraction, divide over here, and I end up with 5 square roots of 2 over 24. And so I've taken this and written it in simplest radical form. Notice I no longer have a square root in the denominator, and everything is reduced. Finally, let's take a look at example 4. We have 2 square roots of 8 over 3 square roots of 2. Now, I've said several times the first thing you should do is check to see if plain old division takes care of the problem. Look what happens here. 8 divided by 2 is 4. Plain old division took care of the issue. There's no more square root in the denominator. And as a result, there's no reason for me to rationalize. Square root of 4 is 2, so I have 2 times 2, which is 4, and I have my 3 in the denominator. So the lesson here is always try plain old division first. It might take care of your problem. If it doesn't, then you may have to rationalize. Please pause the video here and try the next few examples. Let's take a look at the answers. In example 5, we had 20 square roots of 5 over 5 square roots of 8. I could divide the outsides, that became 4 and 1, but my square roots didn't simplify. I still have the problem of a square root in the denominator of my fraction. And tradition says I don't want to have that. So I take the number under the radical, radical 8 over radical 8. That gives me square root of 40, and I brought the coefficient 4 back over, and the square root of 8 times the square root of 8, the square root of 64. Now I simplified the radical, so square root of 40 is 2 square roots of 10, and the square root of 64 is 8. 4 times 2 is 8, the 8's canceled out, that left me the square root of 10. On example 6, same thing, my coefficients reduced, but nothing happened with my square roots. I'm forced to use the method of last resort where I have to rationalize. And so that's what I'll do. Square root of 3 is down here, so I'll use the square root of 3 over the square root of 3. That gave me this right here. There's my perfect square in the denominator, so I'm feeling pretty good. Simplify the square root of 96, I end up with 32 square roots of 6 over 3. And now I can go ahead and see if I can reduce further. I cannot, and so 32 square roots of 6 over 3 is my final answer. Number 7, something beautiful happened. Not only did my coefficients reduce to 4 and 1, but my radicals reduced. This one and this one reduced to the square root of 8. Regular division took care of the problem, and so I don't have to deal with that method of last resort. I don't have to rationalize the denominator. I'm left with simply 4 square roots of 8 on the top and 1 on the bottom. I simplify the radical and I end up with 8 square roots of 2. Finally, example number 8, we have 1/3 times the square root of 7/10. Now remember, when we learned about division, we saw that we could break it into 2 square roots. So this is the square root of 7 over the square root of 10. Regular division doesn't do anything to help me, so I'm forced to rationalize. Square root of 10, so I'll do square root of 10 over the square root of 10. That gives me the square root of 70 over 3 square roots of 100. There's my perfect square. I'm really happy. That's 10. 10 times 3 is 30, and the square root of 70 does not simplify. So here's the lesson to be learned today. Rationalizing, we really do it just from the old days, where long division was difficult to do. Yet we continue the tradition today. Rationalizing means we want to get the square roots out of the denominator. And we do that by identifying what the square root is down there and multiplying by a special number 1. We only rationalize as a method of last resort. Always try regular division first, and maybe, just maybe, that will take the radical out of the denominator without any extra work.